Good morning, students. Today we will continue our topic, that is the chemical properties of alcohol and phenol. In our last class we have discussed the reactions which involve the cleavage of O-H bond in the alcohol and phenol. We have started the acidic nature of alcohol, and from where we concluded that at the end that alcohol are weaker acid than the water, and the phenol also show the acidic nature, right? And their acidic nature is because of the minus I and minus R effect of the benzene ring, right? So today we will discuss about the effect of substituents on the acidic nature of phenol. Now students, the effect of substituent will depend upon effect of substituents on acidic strength of phenol depends upon the nature of substituent, that is whether it is electron withdrawing or electron donating group. So let's first consider here that if we have electron withdrawing group. Now student, the electron withdrawing group, right? Let me consider here the example of NO2 group. Right, we have got carboxyl group also as an electron withdrawing group. Right, so the electron withdrawing group student, it just pull the electron cloud from the benzene ring, right, which has finally been pulled from the O-H, right, bond, which makes it a polar in nature and facilitate the release of the proton and make it a acid, or it increases the acidic strength. So electron withdrawing group, it increases the polarity of O-H bond through minus I and minus R effect. Right, so now let's compare it. Now if we have, this is the phenol, another we have orthonitrophenol, next we have here metanitrophenol, and another is paranitrophenol, right? So if we just get these numbered as 1, 2, 3 and 4. Now student, here the electron withdrawing group is not present in phenol, right? It is not present in phenol, that means it is going to be the weakest among this all, right? So we will place it as 1. Now next come the meta position, that is the third position student. Now the next position student is the second position, and the strongest among this is the fourth one, that is paranitrophenol. Among these four students, the paranitrophenol is the strongest acid, right? So the electron withdrawing group, right, will only work when electron withdrawing effect, it is going to work only when the electron withdrawing group is present at the ortho and the para position. Now if you draw the resonating structure student, from there you will find it down that the electron density becomes rich at the ortho and the para position, and that is the reason that it will be pulled by the NO2 group easily when it is present at ortho and para, right? And the polarity of OH bond will, we can say, the polarity of the O-H bond will increase, and it will increase the acidic strength. So meta will be, among these three, meta will be going to be weaker acid, because here the electron density is not approaching at the meta position during the resonance. Now when we compare second and fourth, that is ortho and para, among these two, which one is going to be a stronger acid, student? So here, student, the generally we say that the due to ortho effect, right? Or here the ortho effect, which we are going to, I just want to correct here, because here the orthonitrophenol is going to be weaker acid than the paranitrophenol. Why? Because here there will be, when the nitro group is at the ortho position, here the hydrogen bond will be functioning here, will come in formation. As a result, the release of proton will get decreased or reduced, right? So at the second one is at the here, right? And the fourth one, student, is the paranitrophenol. This paranitrophenol is among these four the strongest acid. So paranitrophenol, student, is the strongest acid among these four. Now, student, next is the second, that is the electron donating group. Now, student, the electron donating group, like alkyl group, student, we will take the example of alkyl here. Alkyl group, they decreases the polarity of OH bond just by providing the increasing the electron density on the oxygen atoms, right? So these groups decreases the polarity of O-H bond through plus effect and hyperconjugation, right? But more effective, student, will be the plus effect, right? So this one is going to be more effective, or will have greater, we can say, the part responsible for decreasing the polarity of the OH bond. We can better explain, we can explain both way, but the preferred one will be the plus side effect. Now, student, here the electron withdrawing group, so donating group. So we will, let us take example here. Like I am again drawing, this is OH, phenol. Here this is the orthocresol. This is paracresol, and student, this is going to be the metacresol, right? So we will just discuss the acidic nature of these phenol. Now here let us number it as 1, 2, 3 and 4. So here, student, the electron withdrawal donating effect is not going to work where? It will not work in phenol, right? So this is going to be the strongest acid. So here the phenol is the strongest acid. Now again, the electron, whether it be electron donating effect, student, or it be electron withdrawing effect, student, it works better when the group is present at ortho and para position, right? So here the meta, it is a meta position here. So here the acidic strength is not going to get reduced by the position of CH3 at the meta position. This is 4, and now comes the turn of which one is going to be the next one. So student, here if we see the ortho and para, here since we are considering the plus I effect to be more effective, that time the electron donating effect of the alkyl group, it is better explained through the inductive effect, and the inductive effect depends upon the distance of the group. Since the CH3 group is more closer at the ortho position to that where it is going to get its effect working, right? So that's why it is going the ortho one. Here the acidic nature will reduce to maximum, right? And here comes the third one. So here, student, is it this is there. So if we see this one, the presence of electron donating group, so the phenol which doesn't have any of the electron donating group will be the stronger acid, followed by the meta one, right? and then comes the para one, where the electron donating group is present far away from it, and since the CH3 group is just closer to the OH group where it has to play its role, so it is going to play its role, or its effect will be more pronounced, right? And O dash H bond, we can say that the bond cleavage will be reduced, right? And hence it is going to be the weaker acid. So here we have completed the effect of the substituents on the acidic nature of phenol. Now students, we will next discuss the esterification. Students, our next topic is esterification. It also involves the breakage or cleavage of the O dash H bond in alcohol. Right, so let's start with the first one. There are different methods of formation of ester, and the first and the foremost, which one is common, is from the carboxylic acid. So this is our COH, this is carboxylic acid. Then it's get reacted with our alcohol, right, in presence of concentrated H2SO4, which provide H plus ion. This is occurs at equilibrium, a reversible process, and the student cleavage of this O dash H bond take place in the alcohol, and an ester is formed, RCOR dash, along with the formation of water. Right, now what is the role of the concentrated sulfuric acid here? It is acting as a protonating agent which provides a proton for the reaction, and also as a dehydrating agent. It acts as a dehydrating agent. That means to speed up the reaction in the product formation direction, the water which is present here, it has to be removed quickly, right? For that reason we are using sulfuric acid, because along with the protonating agent, it is acting as a dehydrating agent also, and if it gets removed, water is being removed, student, then from the Le principle, the reaction is going to proceed in the right direction, that is in the forward direction, right? So this reaction, this is the first way of esterification. This reaction can also be shown by the phenol also. This is phenol. Right, now let's take an example of CH3, CH2OH, this is ethanol. So this reaction is being carried, so we will get this bond will be broken down, right? And this complete removal of OH group is there, so it is minus water, and student here the CH3 CH2OH will get their O CH2 CH3 will be linked to it, right? So phenol, we have got, this is phenol, sorry, I have got this reaction with the ethanol only, but it's actually the ethanoic acid I have to write here, so slight correction here. So it is student CH3 CH2 C double bond O OH. So from the phenol also it is O dash H bond that will be broken down, and we will get an OCO, it's OCO CH2 CH3. So it is CH2 CH3. So here it is phenyl propanoid which will be formed, right? Now students, the next is when alcohol is going to react with the acid chloride. So it is ROH plus acid chloride, that is CH3COCl, right? So it is RCOCl, and this reaction in presence of pyridine or pyridine, right? So we'll get this bond broken down, that is O dash H with this one. So what we will get? We'll get here R This is CO, this part, right? And then again we are getting here O, and this is R. Again an ester will be formed. Same student will be the case if we use the aromatic ring. So then just write it AR, this OH. So it is RCOCl. In case presence of pyridine, it will form, this is there, ArCO, this is there, O-H, this is OrCOR. Again an aromatic ester is going to be formed. Next students, the reaction is when alcohol, this all are coming under the heading student esterification, this formation of ester. Now next is when alcohol, it reacts with acetic anhydride or acid anhydride, right? So here let us, it is RCO whole twice O, right? In this is acid anhydride. So in this case student, we will get RC double bond OR plus it will get RCOH and acid will be formed. Let's take an example here. If we have taken CH3 CH2OH, this is there plus if you have taken acetic anhydride CH3 this way CH3CO, this is CH3CO. So for convenience, let me write it in this way. It is this. This is acetic anhydride. So from here student, this O-H will come from here. So it is CH3COOH. Right? So we will get here acetic acid form CH3COH. And the next one which we will get is here CH3, CH2O, C double bond O, and this is CH3. Right? That is ethyl ethanoid. Again an ester is being formed here. Now student, these are all the reactions which are named under the esterification. Now student, next we will discuss the reactions where students we get O-H bond C-OH bond broken down. So next category of the reaction student is the reaction involving cleavage of C-OH. That means we are talking about this bond, that is C-OH bond breaking. So students, here the reaction involving the cleavage of C-OH bond. So here students, we have got tertiary alcohol, secondary alcohol and the primary alcohol, right? So on tertiary alcohol student, this is the primary alcohol and this one is, this is the secondary alcohol and this is the primary alcohol. Here, the presence of the 3 alkyl groups in the tertiary alcohol, it increases the polarity of the C-OH bond and hence increases the reactivity. So due to plus I effect of alkyl group, polarity of C-OH bond increases and hence reactivity increases. So among these three, most reactive, right, for the cleavage of the C-OH bond is student tertiary alcohol, followed by the secondary and then the primary. Now let's see here the reactions which are there for the cleavage of the C-OH bond in the alcohol. These reactions, students, they have done in the haloalkane unit. So if hope so you remember it, right? The first is reaction of alcohol with halogen acid, right? So if you take CH3, CH2OH, it has been reacted with HCl at in presence of anhydrous ZnCl2, which is also known as the Grove's process, and this is the Lucas reagent anhydrous ZnCl2 plus HCl. Student, we have to heat it up, heat this reaction mixture, and then we get a haloalkane formed here. Right. Whereas if we take the secondary alcohol, here also, student, we are using anhydrous ZnCl2 and heating, right? So here also we obtain the haloalkane, right? And it is minus H2O. Here also is plus H2O that will be formed. So this is the CH3 which is formed here, and it has got the alkyl group. It is methyl, right? Chloro, it's completely is chloro ethane, which is going to be formed. We have actually CH3, CH2Cl, but it is 1, 2 at one position we have got the methyl, so we can write it 1 methyl chloroethane. Okay, now next is CH3C tertiary alcohol. In case of student tertiary alcohol, we don't need to heat also this reaction. If we have added this ZnCl2 anhydrous, the reaction takes place very fast. Right, this is the evidence for the statement which we have given there, that the tertiary alcohol, they are very reactive. Even on just coming in contact with Lucas reagent, the turbidity or the white precipitate or white PPT formation of the compound takes place, right? The presence of haloalkane, right? Whereas a secondary alcohol takes nearly 5 minutes, 3 to 5 minutes time to get the turbidity form, and the primary alcohol, they will not show any turbidity how much long we stand it up until and unless we get the reaction mixture heated, right? So from here we can conclude that the tertiary alcohol, they are more reactive toward the reaction when the cleavage of C-OH bond is concerned. Now one more thing here I want to tell you, that the primary alcohol, student, will undergo SN2 mechanism, right, for this reaction, and the secondary and tertiary, students, they are going to follow the SN1 reaction, right? So primary alcohol will follow the SN2, and the secondary and tertiary, this one is going to follow the SN2, and this secondary and tertiary, they are going to follow the SN1 mechanism, right? So this is about the reaction of alcohol with OH group. Similarly, students, we have the another reaction, that is the involving a reaction of alcohol with phosphorus halide. So student, here, if you remember, it's ROH plus PCl3 will give here RCl, right? And RCl, if it is getting reacted here, right, it will give RCl plus H3PO3 will be formed, and when it is ROH plus PCl5, you will get here RCl plus POCl3 plus it will form here HCl. Right, so here we were getting here ROH plus PCl3, we will get here H3PO3 along with the haloalkane. Okay, students. So here it is ROH plus PCl5, RCl, PuCl3 and HCl, and it is ROH plus PCl3 gives RCl plus H3PO3. And the next one, student, is the reaction with SOCl2. That is the best method of preparation of the haloalkane from the alcohol. That whenever the ROH gets reacted with SOCl2, thionyl chloride, it will give RCl plus SO2 plus HCl. So since the SO2 and HCl, these are the gaseous products, so the we can say separation become easier. So this was very that time also we have discussed that with thionyl chloride, the product formed, they are easily separated. So hence it is the preferred product, right? So we have discussed today the reactions involving the cleavage of O-H bond as well as the reaction involving the cleavage of C-OH. Yes, students, we will discuss next is the reaction involving the both alkyl group and the alcoholic group, OH group, and we will begin with the acidic dehydration. The acidic dehydration of alcohol means that alcohol from the alcohol hydroxy group, or we can say the water is going to be getting removed. As a result, an alkene will be formed, right? So here just see this. This is an ethanol. I have written it in the condensed in the structure formula. This is CH3CH2OH. So when an acid has been added to it and the temperature, student, is very much specific, it's 443 Kelvin. That time this is there a hydroxy group, that is alcoholic group, is getting utilized, right? And the alkyl group, the whole of the alkyl group, it is getting used up, and water will be released, and we are going to get an alkene. Similarly, students, if we have the case here, I have written here butanol, CH3CH2. Okay, so it is getting 5 here. So we can do with the 5 alcohol also, but here I have, this is there butanol, right? In this case, student, we can either get this hydrogen getting removed with this OH. So that time, student, we will get here CH3 CH2 CH2. This is getting CH, and here it is double bond CH2, right? This is the first product, that is but1E. The chances are there that this HOH get removed with this OH group. So that time, student, what we are going to get? We will get CH3. This is CH double here, student. What will be there? That time this OH that is getting removed, we will get here CH3. So it is here what is getting formed here, that is CH3 CH double bond CH3, right? That is but2E, right? So students, here we will get the product, that is but2E. Now here we are going to apply, student, Sebzep rule, right, to determine the major alkene that will be formed. So student, here the major alkene that will be formed is going to be but2E, because it is maximum alkylated, right? Right, now students, we will discuss the mechanism of the acidic dehydration of the alcohol. So coming to the mechanism, the first step, student, is the protonation of alcohol. Now let's take it with CH3. This was CH2 and this was OH. Right. So here the proton from an acid at 443 Kelvin temperature, it will just get attached to it So here it is oxygen, this is H, already it was having, this is another H, this is the oxonium ion which we are getting. It is said to be still considered to be ethyl alcohol 2 carbon atom, which is ethyl oxonium ion. This is the oxonium ion. Oxygen is getting the positive charge, right? Now student, the next step, that is the second step, is the removal of water, H2O. So we have here in this way. Now the water will be removed. For that, this bond is going to be broken down, right? So here we will get now, it is, we are getting student here, our carbocation is getting formed. Now the third step will be the removal of proton H+. It is in this way, right? So proton will be removed. Students, here though I have shown it with simple bond, actually we have this H. So here this bond will be broken down and this electron is going to complete the valency of the hydrogen. So in this way we will get an alkene formed up, right? So the mechanism of the dehydration of alcohol, it starts from the protonation of the alcohol. We will get here oxonium ion. Then there is a formation of carbocation by the removal of the water. So you can also write it as formation of carbocation. The carbon is getting a positive charge. And once we get a positive charge formed on the carbon atom, then there will be a removal of proton from the adjacent or the nearby carbon atom, right? And here the alkene is being obtained.